Okay.
So welcome everybody. My name is Christian Hernandez Negron, and today we're going to have our first Wind Energy Fellows seminar. And today we have here Dr. John Hall. And so Professor John Hall completed his undergrad degree in mechanical engineering at Missouri University of Science and Technology, where he was recognized as a General Motors Scholar at ASME, American Society of Mechanical Engineers, International Gas Turbines Institute Scholar. He then worked in the power generation, automotive, robotics, and semiconductor industries. Through his professional work experience, he held senior level positions in design, manufacturing, maintenance, and reliability engineering, and obtained a professional engineering license. Following his work in industry, he completed master and doctorate degrees in mechanical engineering at the University of Texas at Austin. During this time, he was awarded a Cockrell College of Engineering Fellowship. His research concentrates on design, methodologies, and novel control techniques that promote sustainability systems, are critical elements of the studies in computer-based simulation that combines concurrent engineering with cyber-physical social system. Key aspects of the work are system adaptability, productivity, reliability, and maintenance. The goal of his work is to develop commercial products that improve the quality of life. Dr. Hall is interested in the applied area of renewable energy system. His work has been published in ASME journals and recognized with distinction at the International Design Engineering Technical Conferences. So without any further ado, the floor is all yours, Hall.
Thank you very much, Christian, for the nice introduction. So hello, everybody. My name's John Hall, and I'm a professor at University of Buffalo. And today I'm going to talk about concurrent engineering with intelligent systems and how we use that to achieve sustainable solutions. So a lot of the emphasis is going to be on wind and renewable energy, just integration as well. So I think Christian, he already gave you a background, but I've kind of got a quick summary here. I was a farm kid. I grew up on a farm, always working on equipment. And so mechanical engineering was a good fit for me. I worked, a few years in industry, and I was a design, manufacturing, maintenance, project engineer, and like Christian said, I got my license. And after that, I went back to the University of Texas. I did my doctoral work in renewable energy. I studied the drivetrain. And while I was there, I picked up a few awards along the way and decided that I wanted to be a professor where I could do research and teaching. So really, whenever we talk about concurrent design of intelligent systems, what we're really just looking at here is it's just like a bird's eye comprehensive view of the system and how it functions over its life cycle. So that's basically what it is. And so if you look at like the system that we have, so I know this from working in industry, like typically in a company, you're going to have manufacturing, you're going to have a design group, and then you're going to have the control group. And the same is true of the system, you have these concerns, manufacturing, engineering, and then how it operates once you deploy it. And a lot of times, these different groups, they tend to work with not necessarily understanding all the constraints and the relationship, that these areas have one another. But nonetheless, these areas, they are related. Like for example, as a design engineer, whenever you put a tolerance on a particular part, the manufacturing engineer, and sometimes these decisions are arbitrary. And so the manufacturing engineers, they're going to make sure, that tolerance is held, to 5 thousandths, 2 thousandths, whatever is said. And, that may mean that they have to take it and, put it on a different machine or something else like that. So whenever I worked at a company that's now Siemens Electric, and whenever I worked there, I dealt with a lot of glass insulation parts. And, a lot of times, like some of the machining on this was pretty precise, and we had to have like secondary operations. And really by working closely with the design engineering group, we were able to understand, we were able to understand like what their needs, like for example, one of the things that we would do is we would take these parts and put this really nice precision cut on the top of these glass parts. And these were parts that were used in these large generators to, to hold, like stator coils in place. And so this required, like a precise machining operation. And the reason they put that on there was simply because there were operators that whenever they were installing these parts, they couldn't have sharp edges where they would cut their hands. And so, by understanding that, that what the need was, we were able to say, hey, well, we got a manufacturing process, where we can do this a lot easier, and everything's still going to be protected. And basically, so we took this operation of these parts, for example, and it would take like 4 days to make these, and we got it down to 4 hours. And whenever you're in the power generation business, like, whenever a city, municipality, whenever they lose power, they're scrambling to get parts. And so by doing that, we were really able to increase market share. And that's important, okay? So that's the system level that I talk about. But this system, it exists in this, in this worldly environment. And like and the system, it's going to have an impact, like cars have an impact on the environment, right? Well, the environment, like for a wind turbine, wind, the way that the wind moves and the nature of the wind, that has an impact on wind turbines, the life of a wind turbine. The same thing with society. We know, and I'll talk about this later, that energy improves quality of life. But the way that we use energy, that also impacts the system, right? So whenever somebody turns on a light switch, runs their washing machine, their dryer, whatever, that's a choice that they make, a human choice. And that choice, that goes back through the through the power grid, and it, increases demand, and it manifests as electromagnetic torque in the system. And that electromagnetic torque, it causes wear and tear. And so you see human behavior, understanding that, like when and how people use electricity, it's really important to the design of systems, and for example, the way you drive a car, it's going to determine how long, the life of it is. And we don't really necessarily understand that. So some of my work, we'll talk about that in a minute, involves qualitative information. And then this is all important because if we want to have products, if we believe that wind energy is something that's really, important to our existence, if you're concerned about climate change and we want to deploy, wind energy systems and improve the environment in that whole situation, we have to make products that people will embrace. And so that's where commercial deployment comes into play. And so really, like these areas, they're all very closely tied to the system level. And there's all these very complicated, relationships, like the components you choose that can cause failure, and that can, impact, availability of energy and the way that it's used. It can come all the way back to the system and affect, wear and tear on a particular component. And so basically the way that we approach this is we're using right now with intelligent systems, we want to gather as much information from these, from these systems as what we can. And so that's where, like data analytics comes into play. And then, we can begin to understand, this information and use machine learning to begin to, come up with a mathematical basis for that. And then having that mathematical basis, we can start to use computer-based modeling to understand these systems, and not just the system, but the operating context as well. And then whenever we understand that, we can, do a better job of engineering design. And so my interest is in, sustainable, systems. And so, in 1987, the Brundtland Commission, they came up with the definition of sustainable development. And basically there's 3 pillars to this platform. Like society, what we want is we want to buy products, that make us happy, that are productive, that are reliable, things that we want, things that we can afford. For the planet, whenever we make something, whenever we engineer something, we don't want to bring harm to the planet, and not just whenever we, get materials and energy to build it, but over the life of the product as well. And then finally, if we're going to, get this stuff out into the hands of the public, our research innovation, we have to come up with ideas that are innovative, that are feasible to build, things that can be deployed. And then, the companies that build these products, they want to make some money off of it. So we have to keep these things in mind. And so really the work that I've done I started in renewable energy, looking at the drivetrain, and so basically, it's all this. A lot of the drivetrain issues are the same for wind, hydro, tidal, and but what I found out was to resolve these issues, you have to get into the blades, and understand the blades, how those are controlled, and the blade design is going to impact, like some of these trade-offs between energy production and reliability. So we have to understand that better. To understand wear and tear and energy demand, we got to get at the grid level and understand, how, when, and why, energy is being used and how much. And then there's also this really complex relationship, at the farm level that wind turbines have with one another, like downstream wake, for example. And so all of this system, within each one of these areas, there's connectivity, but these areas are also connected holistically. So let's talk a little bit about wind energy power curve. This is basically the standard that's used to define the performance of a particular wind energy system, but they all generally look the same. So I think a lot of you guys have probably seen these. This is the power curve. Regions 1 and 4, we don't really get into. That's whenever the power is below and above what the system is designed for, so there's no operation. Whenever we're in region 2, we don't have enough power in the wind. We have enough power in the wind whenever we get to cut in, but we don't have enough to run it at full capacity. So we're between cut in and rated speed in region 2. And at this point, what our goal is to try and capture as much wind, to try and extract as much energy out of the wind by whatever means we have to boost energy production. And so the way it typically works in region 2 is variable speed control. In region 3, we now have, we've reached the wind speed where it's great enough, to produce full power. And if the wind speed goes up over the rated speed, now we've got too much and we can burn up the generator. So in region 3, what we're doing is we're actually using, we have to have some type of mechanism in place to dissipate some of the power. Pitch angle control is what's used, on the large commercial wind turbines that you see. And so basically they pitch the wind, the blade angle to, make it less efficient. And so they hold it at full power. Now I'm going to show you guys, this is some of the early research in the slides coming up here that I did on a simple, one of the early systems like 40 years ago, but it's really good tool I use it in my class for teaching, and it's kind of good for research whenever we're trying out ideas as well. But basically, wind energy control always works through, if you look down in the bottom left-hand corner of the slide, you see that variable CP. And that variable, it looks really simple on this, but there is so much to that, by way of control. And so that's what control works through, is that parameter. And generally, you see that on the right-hand side of this slide. Generally, the way that control works is you see the variable lambda. What lambda typically, represents is the tip speed ratio, and that's just the ratio of the tip of the blade, the wind turbine blade, in relation to the oncoming wind speed, and that's a really important parameter. And then the other parameter that's important is that pitch angle, and so that's why in region 2 we're basically modulating lambda, and in region 3 we're working with the pitch angle. So I'm going to show you a little bit different way that we went about that. So the other factors, and you see these on the left-hand side, that determine the power is the area of the swept rotor, and then also the wind speed, and of course the density of the wind. So this is control. Now this power curve, this is that you see here. Not power curve, the power coefficient surface. This is that variable CP as it relates. There was a formula on the last page, and this is how that surface looks in relation to the speed ratio and the pitch angle. So whenever we cut in, we're typically at the front of this. I don't really have. I don't know. Can you guys see my cursor where I'm running it? I hope you can.
Yes, we can.
Yes,
okay. All right. Thank you. So basically, whenever we're at cut in, we're at this surface. We're in this plane. So we're basically in this plane of the power coefficient and the pitch angle. And as you can see, there's really one point that gives you the maximum in there. And so whenever you're in region 2, and this is, whenever you first start into region 2, you would be hitting it, from the side, and then you're moving back this way as the wind speed increases. And so as you can see, when you're in region 2, there's generally like one pitch angle that's always maximum. So your pitch angle, that's why it doesn't do much in region 2. And then once you get up here, now you're at rated speed, and you need to dissipate some of that. So then you start moving the pitch angle, and it starts moving it down this way on the curve. And so that's why you use the control. Now, the other thing that you can do, and this is what I did in my model. Okay, so you can see there I'm showing pitch control and also speed control. That's basically where we are operating whenever we're trying to modulate those two parameters. So the wind turbine that I'm going to show you in the example, it's a fixed speed wind turbine. It's much different from the ones that you see out there that are commercially available, but it's kind of fun to talk about, and it's very useful for explaining how wind energy works. And so it just has one operating point, and it has stall regulated blades. And what happens is once it gets up into region 3, they begin to stall, and the energy rolls off. I'll show you that on the power curve. But what I did for my so this is my doctoral work that I did like 10, 15 years ago. And so what we did was we took a gearbox and we put it in there. And so we were able to change gears in region 2 and create a discrete set of points. And so this is the system that I worked with for that. And I still use it in my class. I use it for demonstrations like right now. And so basically it just has a 3-blade rotor. This is a 100 kilowatt system. It has a brake like what you would see on an SUV, something about that size. It has 2 gearboxes. One is like a 2-stage parallel gearbox that you see on the left. And then we also have like a variable ratio gearbox, and that was what I added in as part of my work. And then it has an induction generator, again, the 100 kilowatt capacity, a fixed speed. It operates at a fixed speed. And so the only way that we can get to that is through the gearbox. And then we apply control. So now I showed you just had one point. And so basically the way that we're going to be able to manipulate, the power curve is by using the brake and combining that with different gears. So really, to get started, I came up with a model that for this, it involved the power curve, a mechanical system, an electrical system. And the goal for my work was to come up with the design process that would, look at the design and the control. And we wanted to do something that would, use commercially available parts. So improve manufacturability. And so the first thing I did was I modeled it, got a power curve, compared it to what I found in the literature, good to go. And so, started digging in on it, trying to figure out, well, what are you going to have for a gearbox? And so really the work that I did, initially was we said, okay, we have that power curve that you can basically see. It's this lowest one right here. That was the one, the system without the 6-speed gearbox added to it. And so by adding additional gears, that 6-speed VRG, what we did was we created, and this is the final solution that I'm showing here, but we created different power curves, that you would have, but you can't use those because you have to stay within this range. Like the top bar that I'm showing here, this is rated speed, rated power, full power. And the bottom one, what we said was we said, okay, once we get up to rated speed, just all the way across the, through region 3, we don't want to drop below 90%. And so that was where what this lower line represents. And so worked by trial and error, just choosing like different gear ratios. And we found, with a 6-speed gearbox, we're able, to get all the way across region 3 and maintain 90%. The other thing that we did was in the original design, the rated speed, I think was around 17.8 meters per second. And here we've moved it down to 12.8, by adding gears in. And just, this design that we added, I mean, it only really increased the cost of the system like 2 or 3%. And we got like a 6% increase in production out of that, and which is pretty good, I mean, it pays for itself. And so that was the first step. And then we said, okay, now that's without the brake. And so we said, okay, well, let's combine, remember I showed you on the last page, we had those torque curves, and we said, okay, well, let's do a combination of increasing the torque where it would actually be over, 100 kilowatts of power, but we use a brake. We apply a brake, the disc brake in there. And so by the combination of high torque and bringing it back down with the torque, with the disc brake, that's how we get these flat tops across here. And so by doing that, the combination of the lower gears and using the brake, we actually increase it now to 9% beyond the original design. Okay, so then we start getting strategic about this. We use dynamic programming. We run it across different sites. So we got data from NREL, and that was I would run simulation across those where we had different wind speeds. And so really, this is what we want. We want to get it flat, right? We want it to look like that. So those little dark blue areas, we're trying to get all those out as much as we can. Okay, and so we just had like quadrillions and quadrillions of solutions, and we couldn't simulate those. And so, you start kicking stuff out. Like I told you earlier, like anything that dropped below 90%, we said, okay, that's a bad, gear combination. We don't want that. And so that was one of the things that we did to start ruling stuff out. And then, we continued simulating, and basically we looked at, came up with a cost function for this. And the cost function was based on energy production and then that brake design. So what we said was we had like different sites, that we acquired, that we got data from wind data from NREL, and we would run simulation on each of those sites. And overall, the objective was we just said, and this was sort of arbitrary, we said, okay, we don't want to maintain this for 3 years. Now we said 3 years because that was what we had the wind data for. But the point is that we said we don't want to run, we don't want to have to get in there and do any changes. We want to let this thing run for about, we want to let it run for about 3 years without having to change the brake pads or anything. And so that was how we developed this. We have the cost function, that we looked at that. We looked at the amount of wear, the rate of wear. And that was how we got our, and by doing that, I'm sorry, I shouldn't have flipped, but by doing that, we got it up to 12.8%. And so, using our dynamic programming. Now, the problem is at this point, we've been doing this and it's all ideal. So we have gear ratios that you really can't make. So, like you can't have a gear with 12 and a half teeth, right? And so, up to that point, the programming that we've been doing was we're trying to find, like the ratios that would, that would basically work for us as best as possible. And now what we're saying in this step is okay, we found what we need. Now, if we really designed that using actual gears, how close to it can we get? And so that's what this work is. So we had, we had a 2-stage gear train for this. And we looked at like the life of the gears, anything that would fatigue, we would throw out. And again, we ran it on those 20 sites. And we looked at fatigue, like by pitting and by bending stress. And so this is what it looked like. This is what our solution looked like. And so if you see down here, this was just for one of the sites that we worked on. And what you see down in the bottom left is this green dashed line. That's the brake pad over 3 years. That's the amount that's being left over that period. So this is 3 years in this plot. And this is the amount of energy that's accumulated over those 3 years. And so whenever we actually put it into a manufacturable design, we're able to make 12.4%. So we lost just a little bit. We went from 12.8 back to 12.4 when we actually determine what size gears we can use. And if you look at the top right, you can see it's not perfect, but we got that curve, fairly flat. So we still have some valleys in it, that maybe we could work on. And then below it, you see the gear ratios that were used. And then below that, you see the braking that was used, and then the turbine speed. So this is what the commercial solution looked like in the end. It's just like a standard 6-speed gearbox, like you have in an automobile. And then we used an SUV brake, and that was off the shelf. And again, just low cost. I think probably, I think at the time we felt like the gearbox could probably be built for around $300 to $500, and the disc brake would probably cost a couple $100. So that's pretty good, for what we got out of it. All right, so through this work, I realized that, if you really want to have some impact on wear and tear, you got to get into blade design. And so the blade design that we're looking at is for like the Department of Energy, International Energy Agency. They're both recommending like advanced rotor designs that have adaptive features. And so we're looking at this design you see on the right. And if you look in the red box, what you can see here is the blade is twisting. So this is for a morphing blade. And what it's going to do is it's going to improve the wind capture in region 2. It improves efficiency. And it also, with this capability, it's just, the best way to think about this is by having more degrees of freedom. Think about a robot, like with 2 axis. If it was going to try and grab something on a table, there's only really like one path that it can go to. If you have a robot that has 6 degrees of freedom, it can reach around things, obstacles and everything, and pick it up just the same. So the obstacles on this are going to be like vibration. Wind turbines, they vibrate a lot. That causes wear and tear. And typically what we do whenever you get to those, those natural frequencies for vibration is you cut the rotor speed back, or you give up some energy production. So there's always a trade-off between energy production and, loading, vibration, mechanical vibration that manifests as electrical vibration. And, if we're going to floating wind turbines, these issues are really important, stabilizing the system. With this particular design, we can reduce the loading on the system. In region 3, we can reduce fatigue loads by up to 72% with this. So that's pretty good. So we're calling this the twist angle distribution. Now, as many of you know, wind turbines, the blade is twisted. And the reason for that is because you're adjusting the angle of attack of the blade as we're moving from the root towards the tip. And the reason for that is the tip is moving faster through the air. So a rotor both experiences oncoming air, and it also experiences air as the blade's rotating through. And so the tip is rotating faster than the blade towards the root. And so because of that, we're adjusting the angle of attack from root to tip. And that's why wind turbines, that's why they have that twist, that fixed twist. So what we're doing here is we're saying we're going to have a twist that we can adjust. So we can adjust the local angle of attack. So that's our morphing capability. And that's designed by this vector down in the bottom right. Phi, and basically it's defined, that's the twist angle in relation to the distance from the root. And so we had to come up with like some type of design concept for this. And so we took the 2 blades that you can see, the double shear web and the ribbon bulkhead design. We took those 2 ideas and we combined those. And what we have is we have this spar that's rigid. And then we have these shells or these segments that go around it. And that's where we get the compliance from. And so we wanted to do some testing. So whenever you're developing a new idea like this, you have to look at, can we build it? Okay, yeah. So can we make it? Can we build it? And even, you can make an adaptive structure, but if you don't know what you're doing, then you're wasting your time. So not only can you build it, but can you model it? Can you engineer it the right way? Like how do you know what shape is required to, to reduce loading? And then if you can do that, well, does anybody care? And so that's what we're really tackling, in this problem. So we got some data from National Renewable Energy Laboratory, and we looked at this system. It's just a 20 kilowatt system. And the reason we chose that is because there's a lot of data known for this system. NREL's done tests. It's the S809 blade that maybe some of y'all have seen in your work. And so it had pretty reliable results. And so we had to look, and over on the right-hand side, what you see, we had to look at the aerodynamic design, and can we build it mechanically, and how would we go about doing that? And so we started with blade element momentum, and that was, that's a fairly efficient, modeling model that we can use, to get the torque and the thrust loads, but it's not as accurate as CFD. So we started with BEM, and then we use CFD, and you're seeing some of the CFD set up on this. We use that to validate or verify our results. Now, to be able to make it, that's what you're looking at on this slide. So whenever this thing twists, we studied region 2, and we said, what different twist angle distribution are we going to need in region 2? So we broke region 2 up into a discrete set of wind points, like 5, 6, 7, and all the way up to around 13 meters per second. And so we broke it up at that, and at each wind speed, we determined, what the TAD shape would need to look like. And so this isn't just basic, like morphing, where you're changing from one shape to another. It's where you're taking, a morphing structure and you're passing it through a series of shapes. So that's fairly challenging. And so what we did was we got this shape by varying the stiffness within these different sections of the blade, and then by where we place the actuators. And so by doing that, what you see over here on the top right, and this is just for like a particular wind speed, I don't know which one it is, but at each wind speed, we looked at like what the ideal twist angle distribution would need to be for efficiency. And then we said, okay, by this combination of stiffness and actuator placement, how well are we going to be able to match that? And so we matched that as closely as we could. We did a pretty good job of it. And basically our increase that we found was at cut-in, we're going to have a 3.7% increase, and at rated speed, a 2.5. Now that's for this S809 blade. And we also did work with, it was called the 27 AWT. That was another model that we looked at. And at rated speed, we got 14% increase on that, which is that's tremendous. So, different blades, you're going to get different impacts of this. The point is that, it's a good idea and it's a good way to control it. I really think that a lot of the benefit that we're going to see here is going to come from the loading. But here you can see this is what we got in region 2. And like I said, in region 3, we've demonstrated up to 72% reduction. Now, the other question that we had is okay, so we have some understanding now about like what type of range of motion is needed. And so in this particular, I think each one of these slides, they kind of correspond to different papers that we've written. And so on this one, what we did was we did like a CFD fluid structure interaction. And we looked at like, as the fluid hits the blade, that combination of aerodynamic loading with twist, how much deformation do we have in the cross-sectional area? Because if it deforms the cross-sectional area, well, we're gonna have problems. And so our design, it was good. So there was minimal deformation. It wasn't significant. And on this bottom plot right here, what you're actually seeing is those two plots, one on top of the other. And so anyway, this is the control for it. And basically it tells like what the actuator, not where they're located with respect to the blade, but how much actuation they have now. And so this is the control algorithm for that. And then the other thing that we did was based on how much movement we're having, in this blade, you have to pick like a spring, a free position, where it's going to be. And you want the free position, the unloaded position. We wanted to select that based on, minimal actuation. So you would look at like, over the profile of, within the power curve, like where you were going to be moving to the most, and you would probably, position it closest to that, so you minimize your actuation. And so that was the criteria that we used for that. And so we had we came up with an idea that, we could commercialize. We got a patent, got a startup company out of this. These are the papers that we had. We had IP. We're working with Siemens Gamesa on this. So they're interested in what we're doing. But the problem is this thing, it's really computationally expensive. And so you guys have probably heard of Danish Technical University. They had a report last year that basically came out and said something that we had already stumbled across, which is, if we're going to have these, really cool rotors with adaptive features, we got to be able to control those in real time. So we need high fidelity models that are computationally efficient. So we started getting into machine learning for that. And that's the basis of some of the work I got into cyber physical systems. So I think the way that we're going to have to control this is like a digital twin. We have some idea of like what the shape should be, but we expect that we could deploy this and then, improve the control over time. So the other thing that we got into with the digital twin is understanding, like these social issues. So I talked earlier about energy demand, the way that we use energy that impacts, wear and tear on the system. This project, that I'm going to talk about briefly here was a few years ago, I went to India. So this is solar power. But it gets into like the relationship between energy and quality of life. And so in India, some of these communities that I worked in, they didn't have any power. And we went over and helped them deploy, solar power. And what that does is it gives them lighting, like there's snakes in these communities, and at night they have lighting now, which makes it safer. They have agriculture. They're able to start, having businesses. They have education. It supports education, kids can study at night now, tourism, and just the energy that they use there. I mean, by rural, like a rural setting is going to be much different than the way that we use energy from the cities. Okay. Now, keep in mind, this is a microgrid. It's way, located way far away from like a centralized grid. And so this was a microgrid that went in there, a smart grid. They had all these really, really cool features, like they could turn power off at different households and businesses, and they could ration it out. Problem is they got all these really cool features, but they don't have any formalized way to, turn power on and off, like the criteria for that. And so that was where we came up with this idea of quality of life. We began understanding, like what it was being used for. For example, like power for filtering water is probably more important than say, like having power in your house to, maybe run a fan or listen to a radio or something like that. And so we started, looking at what, was most important. But even though they had the smart grid, since they didn't have this protocol like I'm talking about, it didn't work. And it didn't last either. They took it out because the people were so unhappy with it. It couldn't be sustained. So that was, the impetus for our research. And we went over, we helped some of the other communities. And we came up with a controller, and the controller was based on quality of life, how they're using electricity. And basically we came up with different parameters that we evaluated quality of life, like education, access to water, security by lighting, leisure, like being able to watch TV. And so what we look at is we look at like, okay, what do you want? We go into these communities and we work with these folks, what's important to you? And like in some communities, depending on like how deep the water table is, how many people are, like how much sunlight you have, it's harder to get water in some of these than what it is others. And so we came up with, a way to evaluate this, and then we put it into a controller, and we began to look at, like how energy was impacting the community. And this is something called system dynamics, where basically we would study, power and look at the impact of it. And we had, microgrids over in India, so we were able to look at it and, and validate, the system dynamics. So this is a bond graph. Some of you may have seen that. This is the model for the technical system. You can use this to model a wind turbine. You can use it to model a microgrid. And so what we did is we took on the right-hand side, like the community dynamics, like human behavior, and we combined that into this technical model. And this is just what it looks like. System dynamics, we can see how it improves fulfillment. This is a problem where we would look at trade-offs, and this is how we would determine, how we ration out power. This is just an example, that we had here. We looked at different parameters. We looked at water, security, and like household use. And so in the bottom right-hand corner, you see like that's the feasible region, that we could, where we could, make our selections of how much we're going to, ration out. So this is some of the work that came out of that. And so basically, I've went over this. I'm not going to go over this slide, but this is work that our idea, we presented it to the Department of Defense. They're interested in having, like bases way far out, and they are interested in sustainability because they don't want to have to, be carrying fuel and everything. And so a lot of the problems that we've done here, they're very interested in renewable energy. And so this was something that we laid out for them, like the adaptive blades, how that could improve the energy, the performance of those systems, and then also how they could use, like power management. And that was some of the work that I showed you based on the quality of life. And so like the work that I do, as a scientist, my research, a lot of folks, they do basic research. I tend to do a range of basic all the way to applied. We talked about the qualitative information that goes into this, industry 4.0, cyber physical social systems framework. It supports concurrent engineering. And then, we use concurrent engineering to, work on phenomena like fluid structure interaction. I showed a little bit of that. And that's how we make adaptive structures. And then we put those adaptive structures in renewable energy systems. So that's kind of how my research comes together. This is some of the ideas, that my students are working on. Like, we can also use that TAD, not just to improve efficiency and loading, but downstream wake. So that's something that we're currently working on. That's really an important issue. We're using a digital twin to try and understand this. And so, like what the TAD shape should be. We studied it for efficiency, but now we have to look at more trade-offs. And then also we have like the modeling of qualitative information. And so this is basically how we take qualitative information. I was talking earlier, like wear and tear on a car, like somebody drives a car really, really hard, or they use a lot of electricity. Well, how do you define that? How do you organize that into some, quantitative, framework that we can use, for this type of engineering design. So I just want to give credit to my wonderful students. These are students that are currently in my lab. Philippe, Haley, James, and Schumann, and Eric. Eric's actually an undergraduate. He's had 3 papers, 3 book chapters this year. Haley's a National Science Foundation Graduate Research Fellow. She graduated, so she's now Dr. Suk. And so I'm really proud of my students, and I just wanted to introduce them to everybody. And that's the work we've done this year. We have an NSF grant that we're just waiting to come through anytime. And this is some of the contributions. So I'll just leave that right here. And that's pretty much it. So if you guys have questions, I can take questions.
Thank you very much, John. I think we have like time for questions. If any in the audience have questions, we will be happy to take those. Mike? Yeah, you have to ask me.
Did they put them in the?
Oh, cool. Okay. Hi, Professor Hall. Thank you for the presentation. Very interesting. I actually have 2 questions, and one is both go into different topics. The first one is you presented a brake system in order to kind of in addition to the gear system, in order to finagle the power curve to keep operating at its maximum capacity. I was wondering, like, was there any sort of like heat dissipation system or anything like that? I can imagine there's a lot of heat generated, and I heard the turbines like catching on fire because the system, the wind was so strong and forced the brake to the turbine to spin despite the brake. So I imagine, like, was there any heat dissipation that worked its way into the design?
So that's a really good question, Michael, and it's something that I didn't mention. But yes, I had a model for that. So that I don't think I show it in this let me see if I do, because I have it modeled. But yeah, there was. I mean, so the brake that I chose was so like the rotors. There's two different types of rotors. There's rotors that are like solid, and I don't know how thick they are, maybe like a 3/8 of an inch thick, something like that. And then you have rotors that are probably a little bit wider, like they may be, you know, like 5/8 or 3/4 of an inch thick. And those are actually in the middle, they have vanes. And that was what I modeled. And so they do have heat. Now, one of the constraints so do you remember how I showed you that area and it was flat at the top, and then what was constraining that was the heat. So there were two things that constrained it, was the heat in real time. And that was basically, if it wasn't for the heat, you could have just left the brake on as much as you wanted.
Right.
But I can't remember what the heat was. I think I want to say it was around 500 degrees roughly. It was in that range.
Fahrenheit.
And really the reason that you control heat is before you actually get to the point where it'll cause a fire, it will actually, like brakes, if they overheat, they don't work as good. That's the nature of those materials that are the ceramic materials used in brakes, is if they get hot, the brakes don't work as good. And so that was the constraint. So, I mean, I was digging up like models on those brake materials and looking at like what the heat would be. And then I had a model for heat, you know, how much heat would be generated based on the pad and the amount of, and then really the way that you can do that is the amount of torque that it dissipates, that's a power. And that's the power that's equivalent to and that power can be equivalent to heat.
Right. And so it's entirely passive. You said vanes, right?
Right.
Okay.
Yeah. But I mean, what would happen is once it got to that point, because I mean, and the model wasn't real complicated. It was just, what I said is I said at this point, that amount of heat that's generated will eventually overheat it. Now, you probably could have had like instances where you said, okay, it's at that point and I can run it at that point for a minute or two and then back off. But that was a headache. What I said is once it gets to that, that torque, we just cut out, we just take the brake off and go to the next gear. That was how I did it. Yeah. But if you actually had a system, you could have a feedback in there and do it that way. Yeah.
So, great. Yeah. And thank
you. Good question. Yeah. Thanks.
I do have another question, but for the adaptive blades, so usually when I think of adaptive blades, they do the adaptive concept by mismatching making the composite layup a certain way such that when you push on it, it bends and twists at the same time. But your concept right here, it seems that, is it using one like material and then changing the structures, physical structure, such that it bends when you push on it, or it actuates, like there's an electronic control, it sounds like, right?
It's actuated. So there's already designs out there that are passive. They call them bend twist couple, and I think I had that on a slide. I kind of went through some of these materials fast, but like they do have a bend twist couple. And I think it's probably on smaller wind turbines. The small wind turbines, they're doing everything that they can because they're trying, to control those, and they don't have a lot of money to put into active controls. So they got all these wonderful, passive solutions, and that's one of them.
is like whenever the wind hits them at a certain speed, the blade will actually twist.
Right.
And in twisting, you know, that's an FSI response, right? So it changes the structure and then it changes the fluid dynamics, and it does it in such a fashion that, you know, you know, it reduces loading. We're just doing it actively.
Okay.
So, yeah. So,
All right.
you know, with active control, you're always going to have better control over it. And
Yeah.
the question is, and that was some of the stuff that, you know, we looked at, you know, when we went into this patent, man, we had to prove all that was, you know, is it worth it, you know? So,
Right. It's the additional complication worth
Yeah.
it with all the motors. It looks complicated.
that's what we always get asked, you know, is, you know, you're adding complexity. And I always go back and I say, yeah, you know, but at some point somebody said the same thing about pitch control. They really did, you know. And you know, they said the same thing about variable speed control. You're adding complexity. But it became, you know, but the technology and everything evolved to the point where we had more to gain, you know, from it than what it cost us, you know, and right, you know, speed control, torque control, region 2. I mean, that's a tremendous, you know, advancement, you know, for the technology. And in region 3, being able to hold the pitch, you know, at full power, that is too. And so these are things that pay off. And so that's what we've done is, you know, through our work, we're saying, hey, it pays off to do it this way too, you know, I don't think the increased efficiencies, you know, I said we get anywhere from like, you know, 3% up to 14. But I think where you're really going to get improvement is these wind turbines, the blades on them are going to be like twice the length of football fields.
Wow.
And, you know, and they just, you know, they can make the blades, that's not a problem, but they're not stable. You know what I mean? And so we're providing, you know, a means that these can be stabilized, you know, and, you know, I don't talk about this, but even stiffened, you know, and so I think all this is important. So I think, you know, that the industry to move forward, like I said, we talked to Siemens and we've talked to is it Ellen Blade, and you know, they're telling us, you know, we don't want to do it right now, but we know we're going to have to. So yeah. So yeah, so thanks for the question. Yeah.
Thank you. Yeah, very interesting.
Yeah.
We're getting short of time, but we can take one more question if anybody have.
Yes. Hi, I have a question, please.
Go ahead.
Yeah. So, what is the status of the research on this adaptive control methodology, like you just discussed, like to get the real-time wind data and then modify the blades accordingly in real time?
Man, it's far from that. I mean, because it's just such a computationally expensive problem. So, I mean, like your BEM that we're doing now, I mean, you know, like if you use the model for it, you know, like you get a wind speed and then you model it, and then an hour later, you know, it would tell you where you need to be. And so that's the need for this. But I think what you're asking, Assad, is you're asking like, how far along are we on that? We don't have it where we need to be, and that's where we're looking at research funding. But we know we're on the right track. You know, you guys are scientists, you know, like students and everything, you know, and so there's different ways that we identify gaps in the research. And for this particular one, you know, like if you read some of the papers, like DTU, they had a report and they said, you know, like high fidelity models needed. That's a gap that they found. We came across it through our work. You know, we designed this and we're like, okay, you know, we got this solution, we can build it and everything, but wait a minute, this model, it's no good. You know, it won't work for control. You know, work for design, because you don't design, you don't need real time, but for control, you got to have real time. So that's where the digital twin comes into play. And so, I mean, I think we're really tackling an important problem there, and I think we got the right way to do it. So stay tuned.
All right, thank you so much.
Well, thank you, everybody. And thank you, Dr. John Hall, for being with us and sharing your knowledge. So
yeah,
we hope to have you next time in person here on campus. So
yeah. All right.
Well,
Thank you so much.
bye.
Thank you.
All right.
Thank you.
Everybody have a
Thank
good
you.
day. All right. Bye-bye.
Bye-bye.